Thousands of years before the first telescope was even a dream, ancient civilizations were predicting solar eclipses with terrifying accuracy. They created star catalogs so precise they could forecast the return of comets and aligned monuments to the heavens with a skill that still baffles engineers today. They didn't have computers or advanced optics, just their eyes, their minds, and a handful of brilliant, nearly lost techniques. So, how did they unlock the secrets of the cosmos and map the stars with such shocking precision? It's one of the greatest mysteries in human history. We see the evidence of their genius carved into stone, written on clay tablets, and built into the very foundations of their cities. Think about the Great Pyramid of Giza, aligned to true north with an error of just a few arc minutes, a tiny fraction of a single degree. Or the sprawling complex of Chichen Itza, a celestial clock where shadows crawl like serpents on the solstices. These aren't just architectural wonders. They're astronomical instruments on a colossal scale. But how? How could our ancestors possess such a profound insight into the clockwork of the universe? They faced a monumental challenge. To chart the heavens, you need to solve three fundamental problems. First, you need a fixed point and anchor in the spinning chaos of the sky to measure everything against. Second, you need tools, instruments that can actually measure the vast, empty angles between stars and planets. And third, you need to see beyond a single human lifetime to spot the slow, patient patterns of the cosmos that only reveal themselves over centuries. Solving these problems without modern technology sounds impossible. Yet, they did it. This isn't a story of alien intervention or mythical powers. It's a story of human ingenuity at its most brilliant. It's a detective story where archaeologists and historians have pieced together the clues, rediscovering the forgotten science of the ancients. Today, we're going to unravel that science. We'll reveal the simple, elegant, and powerful methods our ancestors used to create their breathtaking maps of the stars. Finding a fixed point, the anchor of the heavens. Every map, whether it's of the earth or the sky, needs a starting point. It needs a north, a south, an east, and a west. Today, we have GPS and compasses. But what could ancient peoples possibly have used? How do you find a true unmoving direction on a spinning planet under a wheeling sky? The answer wasn't in one place, but two, one for the day and one for the night. The daytime anchor was the sun, and the tool they used was the simplest imaginable, a stick in the ground. This tool, called a gnomon, was arguably the first and most important scientific instrument ever invented. By tracking the shadow of a gnomon throughout the day, observers noticed a distinct pattern. The shadow shortens as the sun rises, hits its absolute minimum length at local noon, and then lengthens again. That shortest shadow, every single day, pointed directly north in the northern hemisphere or south in the southern. By marking that line, they established the north-south meridian, the foundation for everything else. They could now build their temples, align their streets, and orient their lives with cosmic precision. But the real magic happened at night. While the sun gave them a line, the night sky gave them a single unblinking point. We know it as Polaris, the North Star. To the naked eye, Polaris is unique. As the Earth spins, every other star in the sky appears to wheel in a great circle around a single fixed point, the celestial pole. And Polaris sits almost directly on that spot. For navigators and astronomers, this was an incredible gift. To find your latitude, you just needed to measure the angle of Polaris above the horizon. To find north, you just had to look up. But here's where it gets truly brilliant. The Earth, it turns out, isn't a perfect spinner. It has a slow 26,000-year wobble on its axis, like a dying top. This phenomenon, known as precession, means that the North Star actually changes over millennia. The star we call Polaris wasn't the North Star for the ancient Egyptians. When the pyramids were being built, the celestial pole was near a faint star called Thuban in the constellation Draco. And before that, it was near other stars. So how did they deal with a moving target? They turned a problem into a solution. By watching which stars never set the circumpolar stars that circle the pole, they could identify the empty point in space that was the true center of the sky's rotation. They could then use pairs of these stars, like the pointers in the Big Dipper, to draw a line directly to that invisible celestial pole. The Egyptians mastered this technique with a tool called the Merkit, or instrument of knowing. It was an ingeniously simple device, a plumb line for establishing a perfect vertical, used with a sighting tool called a bay, often just a palm rib with a V-shaped notch. An observer would sit and align their view through two Merkits toward the celestial pole, establishing a perfect meridian line across the night sky. As the night progressed, they would call out as different stars crossed this line. This allowed them to create a celestial clock, dividing the night into hours. But more importantly, it was the foundation of their maps. By noting when a star crossed the meridian and how high it was in the sky, they could give it a precise coordinate. They had found their anchor. With a stick and a piece of string, they had locked down the heavens and were ready for the next step, to measure them. The celestial measuring tools, charting the cosmos. Once you have a fixed point, how do you map everything else in relation to it? The sky isn't a flat piece of paper. It's a vast dome. To chart it, you have to measure angles the angular distance between two stars, or between a planet and the horizon. Without trig tables or laser theodolites, how was this possible? The answer lies in some of the most beautiful and intellectually powerful instruments of the ancient world. They started, once again, with the human body. An outstretched hand at arm's length gives you a rough but consistent set of measurements. The width of your finger is about 1 degree. The width of your fist is about 10. For early sky watchers, this was enough to notice patterns, to see that the moon was about half a degree wide, and to track the slow drift of the planets. But to build the great star catalogs, they needed far greater precision. This need drove an explosion of innovation. One of the most elegant solutions was the armillary sphere, developed by the Greeks around the 3rd century BCE. It was essentially a physical model of the universe. A set of nested interlocking rings represented the key circles of the sky: the horizon, the celestial equator, and the ecliptic, the path the sun, moon, and planets travel along. At its center sat a model of the Earth. The armillary sphere wasn't just a beautiful teaching tool. It was a dynamic calculator. By rotating the rings and using a sighting device, an astronomer could determine a star's coordinates. It made the invisible grid of the heavens tangible. You could see how the sky moved, predict where a star would rise, and understand the geometric relationship between everything in the cosmos. It was a mechanical computer that turned complex geometry into a physical, intuitive process. As these tools evolved, they became more specialized and accurate. Astronomers in the Islamic Golden Age, who inherited and greatly expanded upon Greek knowledge, perfected instruments like the quadrant and the sextant. These were basically giant protractors, often built right into the walls of their observatories, that could measure the altitude of a celestial body with incredible precision. The larger the instrument, the finer the markings, and the more accurate the measurement. But perhaps the most iconic and powerful instrument of the pre-telescopic era was the astrolabe. Its name comes from the Greek for star-taker, and that's exactly what it did. The astrolabe is a work of genius, a 2D projection of the 3D sky. It had two main parts: a fixed plate engraved with a map of the sky's grid for a specific latitude, and a rotating overlay called the redi, which was a skeletal map of the brightest stars. By aligning the redi with the stars you saw in the sky, you could solve an astonishing number of problems without a single written calculation. You could tell the time at night, find the time of sunrise and sunset, or even determine the direction of Mecca for prayer. The astrolabe was the smartphone of its day, a portable, powerful, all-in-one analog computer that placed the power of the cosmos into the palm of your hand. The Greek astronomer Hipparchus, often called the greatest astronomer of antiquity, used tools like these in the 2nd century BCE to create the first great star catalogue of the Western world. He meticulously recorded the position and brightness of around 850 stars. His system for classifying stellar brightness, the magnitude system, is still used in a modified form today. His work was so foundational that it was preserved and expanded on by Ptolemy centuries later in his work, the Almagest, which became the definitive astronomy text for over 1,400 years. The accuracy they achieved was stunning. While the naked eye has its limits, these dedicated astronomers could plot a star's position to within about 1 degree of arc. That's just twice the width of the full moon. They did this by building massive instruments, by taking repeated measurements and averaging them out, and by dedicating their lives to the patient, meticulous work of measurement. They had created a new kind of knowledge, not based on myth, but on empirical data. They had taken the first true measure of the heavens, the patterns of time, decoding the future. Having a fixed point and the tools to measure from it are essential. But the true genius of ancient astronomy, the achievement that feels most like a superpower, was its ability to predict the future. How could the Babylonians, over 2.5 millennia ago, know when a lunar eclipse would plunge the world into darkness? How did Mayan priests create calendars more accurate than the ones used in Europe at the time? The answer wasn't a single brilliant insight or a revolutionary piece of tech. It was something far more profound, the power of patience, and what was essentially the world's first big data project. For centuries, in Mesopotamia, Babylonian priest scholars did something no civilization had ever done before on such a scale. They observed and they recorded. Night after night, generation after generation, they etched their observations onto clay tablets. These weren't poems, they were scientific records. Known as the astronomical diaries, these tablets documented everything: the rising and setting of stars, the looping paths of the planets, the appearance of comets, and most importantly, the exact time and date of every eclipse they witnessed. For the Babylonians, this was a matter of state security. They believed the heavens were a message board from the gods, and an eclipse was a powerful omen. Understanding these omens was a way to control their destiny. But in their quest to read the future, they stumbled upon a fundamental truth of the universe. It is built on cycles. After centuries of piling up this data, an unmistakable pattern emerged. They discovered that the complex conditions needed for the sun, earth, and moon to align for an eclipse repeat themselves almost exactly every 18 years, 11 days and 8 hours. We call this the Saros cycle. By recognizing this pattern, the Babylonians were no longer just reacting to omens. They could predict them. They developed mathematical tables that used these cycles to calculate the future positions of celestial objects. It was the birth of predictive mathematical astronomy. This same principle, the discovery of long-term cycles through meticulous observation, was the key to astronomical achievements across the globe. For ancient Egyptians, their entire civilization depended on the annual flooding of the Nile. They noticed this life-giving flood consistently arrived shortly after the star Sirius, the brightest star in the sky, reappeared in the dawn after being hidden by the sun's glare for 70 days. This event, the heliacal rising of Sirius, became the cornerstone of their calendar. Meanwhile, in Mesoamerica, civilizations like the Maya developed some of the most complex calendar systems ever conceived. They tracked not just the 365-day solar year, but also a 260-day sacred calendar, and most remarkably, the long cycle of the planet Venus. They observed that Venus completes its cycle as a morning and evening star in 584 days, and figured out that 5 of these Venus cycles equals 8 solar years, almost to the day. This allowed them to create incredibly accurate calendars that could pinpoint dates thousands of years in the past or future. Their great observatories, like the one at Chichen Itza, weren't just temples, but stone computers for tracking these vast celestial rhythms. What all this represents is a monumental shift in how we think. These ancient astronomers realized the universe wasn't just a chaotic realm of unpredictable gods. It was a cosmos and ordered, knowable system governed by rules. They understood that if you watch patiently enough and keep records long enough, the universe will reveal its secrets. They didn't need to see the gravitational forces at play. They could see the pattern they created. This was their lost knowledge, not a secret formula, but a profound commitment to multi-generational observation, a scientific relay race where the baton of knowledge was passed from one century to the next. They learned the language of the cosmos, a language written not in words, but in time. The story of how these civilizations mapped the stars is a powerful testament to human curiosity. And that same spirit is what drives us today. If you've been fascinated by this journey into the ancient cosmos, make sure you subscribe and hit that notification bell, because we have so many more secrets of the past to uncover. And let us know in the comments below, which ancient astronomical achievement do you find the most mind-blowing? We read every single one and love diving into the discussion. From a simple stick in the ground to the intricate gears of an astrolabe, from the patient records of Babylonian priests to the monumental observatories of the Maya, our ancestors achieved the seemingly impossible. Without a single telescope, they established the cardinal directions, measured the architecture of the sky, and discovered the great, sweeping cycles of time that govern our world. These achievements weren't just academic exercises. They were woven into the fabric of their societies. Astronomy gave them the calendars to plant and harvest. It gave them the navigation to cross open oceans. And it gave them a cosmology, a sense of place and meaning in a vast and mysterious universe. But their most enduring legacy is the foundation they laid for everything that came after. The knowledge of the Babylonians, Egyptians, and Greeks wasn't lost. It was preserved and enhanced by Islamic scholars, who refined their instruments and mathematical techniques. This body of knowledge then fueled the Renaissance in Europe and the scientific revolution that followed. When Copernicus and Galileo looked at the sky, they were standing on the shoulders of giants like Hipparchus, Ptolemy, and the unknown astronomers of Mesopotamia. Even today, in our world of space telescopes and supercomputers, we live with the echoes of their genius. When we measure a circle in 360 degrees or an hour in 60 minutes, we are using a mathematical system pioneered in ancient Babylon. Many of the constellations we recognize still carry the names of Greek heroes and myths. The quest to map the stars is one of the oldest human endeavors. It's a story that reminds us that with enough patience, ingenuity, and a relentless desire to understand, there are no limits to what we can discover. The night sky is the same one they looked upon thousands of years ago. It's a bridge across time, connecting us to our most distant ancestors, who first looked up in wonder and dared to draw a map of infinity.